Hello and welcome to this course on noise control in mechanical systems with me Professor Sneha Singh from IIT Roorkee, and we have been discussing about sound barriers. So we started our discussion with passive noise control, followed by the various kind of barriers, what do you mean by that, and what is acoustic enclosures, and we also solved certain problems related to that. So in this class we will begin our discussion on sound absorbers. Okay, and we will see what are the things used for evaluating the performance of absorbers. So we use sound absorption coefficient and noise reduction coefficient, and how are these absorbers classified, and what is a typical sound absorptive treatment. So for a quick recap, based on what is your desired intent of noise control and what is the extent of reflection, dissipation and transmission that your material can achieve, the various kind of acoustic materials, they are classified as barriers and absorbers. So what do you mean by absorbers? It is when suppose you want to achieve the noise control near the source itself in this particular place. Okay. So in that case, whenever it is hitting the material, it should not reflect back, because it will just increase the noise source near the medium of incidence or near the source. So absorbers fall under that category where the materials, they have to minimize the reflection. Okay. So how do we define them? These are the acoustic materials that absorb the sound waves, whatever is incident on them, that is, they minimize the reflection of the sound waves. So how do they do this? How do you minimize the reflection? So whenever the sound wave is hitting a material, you minimize it because you do not want it to reflect back. So basically you would like it to pass through. Okay. So these materials allow the sound waves which are incident to enter inside it. Okay. And once they enter inside it, it's up to the case by case. The material can either dissipate the sound energy within itself while passing, and in that case not just the reflection is minimized, but even the transmission to the other end gets reduced, and otherwise they can just allow the material to pass through, the sound waves to pass through the material without any dissipation, and even that could be called as absorption. So typical kind of absorbers, we have these various kind of porous materials like foam, glass wool, even the natural woven fibers, and even like for example we have an open window in a closed room. So whatever I am speaking, it's like a medium continuity. Okay, when the sound waves, they propagate and they reach the open window, they don't reflect back, because the impedance of the medium left side of the window and the right side of the window is the same. So the sound waves simply pass through as if, because it's a continuity in the acoustic medium. So there also absorption is there, and because the entire waves get absorbed, there is no reflection there because it's the same medium continuing, the absorption coefficient for this case becomes 1. And then I took the example of some of these fibers, for example the kind of clothes you wear. If you see your clothes and everything, they have so many pores and holes and spaces in between them that the sound waves can pass through it. Okay. So now you know that these materials, they do not block the sound, they simply minimize the reflection. Okay. So they are more effective. So suppose in any field we had the source, suppose it was a free field environment, okay, and the source was directly reaching the receiver through a direct path without any significant reflected paths, then use of absorber is not going to be very effective in that case, because here it is supposed to minimize the reflection. But if you consider an open field environment, there are almost no reflections. So the use of absorber is ineffective there, it is not contributing anything there. So basically when you have environments with a lot of reflections, there on these reflecting surfaces, if you have sound absorbers, then what it will do is it will minimize, it is going to reduce these various reflections, and it will turn out to be more effective for noise control. So that is why absorbers, they are mostly used in the reverberant environments. So here from a schematic you can see, suppose we have some machinery or some mechanical system which is our source, and these are the receivers. Okay. in the very first case, there is an open field environment and there are no reflections and the sound waves are just emitting like this. Even if you have an absorbing material which absorbs whatever is hit on it, how is it going to affect the sound level? There are no reflections at all. But if suppose it was a reflective environment, okay, we enclose it within a room, highly reflective room, hard walls, and also there are so many structures within the room that are also reflective in nature, let us say. So, now in this case the sound is reaching the receiver via the direct path, then also via some indirect paths, okay, some other kind of indirect paths, let us say many such kind of indirect paths are there and the sound is simply multiplying. Okay. So, now if you use the absorbers and you have the absorber linings on all these reflective surfaces, okay, this is the absorber lined on the reflective surfaces, okay, and all around this wall. Okay. So, in that case what happens now, whatever sound is incident on these reflecting surfaces, it is not reflecting back. So, this path has been cancelled because it is getting absorbed into the material. So, the reflection has stopped. In the same way here also it absorbs and this reflection stops. Here also this stops, here also this stops, okay, and various other reflecting paths. So, now all of these things they have cancelled out, all of these things, and rather we just have the direct field coming in. So, because there were significant reflections which were increasing the overall noise level, and with the use of the absorbers we have cancelled out and removed these various alternate pathways that the sound was taking. So, now the noise level will go down. So, the more reflective the environment there is, the more you have reflections, the better will be the performance when absorber is used. But if it is a free field environment and the reflection at the to begin with itself is very low, then use of absorber is not going to be effective. Okay, so how do you do the evaluation of the performance of the sound absorbers? So, there are two measures, sound absorption coefficient and noise reduction coefficient. Alpha is the symbol used for sound absorption coefficient. We already defined sound absorption coefficient when we were discussing about the acoustic fundamentals, and that was defined as 1 minus mod r whole square. So, now in the context of an acoustic material, what do you call it as a SAC or the sound absorption coefficient? It is the fraction. So, if you see here, this is the fraction of the incident sound energy absorbed by the material, i.e. the fraction of incident sound energy that is entering inside the material. Okay. So, if suppose 1 pascals of sound wave is incident, intensity of 1 of sound wave is incident, how much of it is actually going into the material without reflection? So, the fraction of incident energy that is getting absorbed or entering the material. Some other way to put this is that that whatever energy is incident, okay, it will either reflect back from the material or it will get absorbed and pass into the material. Okay. So, whatever is this, it will become I incident. Okay. So, in that way you can say that it is the fraction of the incident and sound energy that is being lost when reflecting back from the material surface. And SAC is a function of frequency just like all the other measures such as transmission loss, insertion loss and so on. Okay. So, sound absorption coefficient, it is a function of the frequency. It is defined as the sound intensity that is absorbed by the material divided by the sound intensity that was incident on it, and that is 1 minus mod r whole square. Okay. So, obviously, whatever energy that is falling on the material, okay, the maximum absorption that you can get is the entire energy gets absorbed. Okay. And the minimum would be that none of the energy is getting absorbed. So, the alpha value is always going to lie between 0 to 1. It cannot be greater than 1 because suddenly the energy is not going to add it up. We do not have an external source of energy in this material, then whatever is incident, the entire thing, the maximum that can pass through is the entire thing that is passing through without an increase in the energy. So, by the conservation of energy, the value of alpha has to be between 0 to 1. Okay, so how it is derived? We have done it in the acoustic fundamentals module as well. So, alpha is the intensity that is absorbed by intensity that is incident, and we know that if something is incident on it, it will either be reflected back or it is going to be absorbed. These are the two things that can happen. So, I absorbed would be I incident minus I reflected. Okay. Okay. So, if you do this thing here, it will be 1 minus I reflected by I incident, which is simply 1 minus mod r whole square. Okay. So, whenever there is a medium continuity, then SSE becomes 1. So, for example, you have got a hole in the wall. So, for that hole the alpha will become 1 because whatever is incident on the hole, it is simply passing through, the hole is not going to reflect back. Okay. So, the sound absorption coefficient, suppose so sound absorption coefficient is something which is defined as per unit area term. Okay. So, here we assume that we have the material surface of uniform composition, that is having the same alpha throughout, and that for that material surface you define what is the net absorption SAC per unit area. But what if that particular material itself was composed of different materials, each having their own sound absorption? Then for that particular composite material, what you do is the average absorption you can calculate, which is the summation of the surface area of that particular material multiplied by the alpha of that material and so on, divided by the total surface area. So, let us say this particular material had an alpha of 0.8, this had an alpha of 0.9, this had an alpha of 0.85 and this had an alpha of 0.7. And let us say the area was this was if we consider this as 1 meter square, this was let us say 1.5 meter square, this was let us say 3 meter square and this was again 1.5 meter square, let us say, then alpha bar for this particular wall is going to be, you will multiply the surface area with their corresponding alpha. Okay. So, we have done this divided by the total surface area, which is okay. This is what should give you the total average absorption for this complete wall. Okay. Fine. So, now that we know that see alpha is defined as per unit area, okay. It is a fractional quantity, and for a material with uniform composition you can find out per unit area absorption. In the same way, if it is a material made of different things, there also you can find out an average value, which is the fraction of the energy that is getting absorbed. So, it is a per unit area quantity, it has no units. But suppose if you have a material of suppose a certain alpha and you keep increasing its surface area, then the net sound absorption would be whatever is the per unit area absorption multiplied by the surface area. So, that quantity we call it as the total sound absorption, and it is simply S into alpha bar, and the units that we assign to it is Sabine. It is after the scientist who formulated this. So, you simply say that okay, this is the per unit area alpha of a particular wall or a particular surface, and the S is the total surface area, then the total surface area multiplied by the absorption per unit surface area will give you the total sound absorption. Okay. So, how do you define this unit Sabine as? It would be the total sound absorption by a 1 meter square exposed area of a completely absorbing material surface such that it has an alpha of 1. So, so 1 Sabine would be what? S into S is equal to 1, alpha is equal to 1, you will get 1 Sabine like that. Okay. So, the sound absorption coefficient, the measure, first of all it is a per unit area measure without any units, and it is a function of what frequency is being incident. As I told you that alpha is a function of frequency. Okay. It also depends on the material thickness, because this is a per unit area quantity. So, suppose this is the cross section of some material and per unit area it is having some alpha. Then suppose you keep on increasing the width of the material like this. So, for this material the per unit absorption is going to go up. Okay. So, it depends on the material thickness, okay, and it depends on the material's composition. Different materials have different absorption capability. It also depends on the surface finish and the method of mounting, and when we do a discussion on the individual sound absorbers, we will see how this variation happens. Okay, so let us now see the second measure used for evaluating the sound absorption by a material. So, here the first measure was SAC, but SAC is not a single value measure. Okay, it is a variation with respect to frequency. But as a noise control engineer or any engineer, we are always fascinated with having some single value measure just for a very quick analysis and estimate. So, that single value measure here becomes the noise reduction coefficient. Okay. So, what is it? It is a single value measure. So, how do you obtain this? Suppose you have already the alpha versus the frequency. You do the arithmetic average of the measured sound absorption coefficients of the material surface at 250, 500, 1000 and 2000 hertz octave bands, okay, and then you round it off to the nearest multiple of 0.05. So, a way to show this is that, let us say we have some material like this. Okay, sorry, alpha versus frequency I want to see. Okay, this is 250 hertz, this is 500 hertz, this is 1000. Let me draw a larger picture. Okay, so this is the frequency in the octave bands, this is your alpha value, and suppose we have some curve here like this, and we find that at this value your alpha is coming out to be 0.5, here it is 0.6, okay. Then your NRC would be what? It would be we will do the arithmetic average first to find out NRC dash, let us say. So, here you do the arithmetic average, it is a linear 0.5, 0.6, 0.7, 0.8. So, it will come out to be 0.65. Now, you will see whether it is a multiple of 0.05. So, let me here take a case where it is not a multiple of 0.05. So, we can do that like this Okay. So, if you do this, what you will get is 0.65, and one more thing, so it will become 0.1 by 4, so likely. So, then here this is not a multiple of 0.05. So, your NRC will then become, suppose you have found the arithmetic average as this, then your NRC will become the nearest multiple of 0.05, which can either be 0.7 in this case, or it can be 0.65. So, usually the engineers, they choose the upper value and they give, if both are near to it, they give the upper value, okay, and like this they calculate it. Now, how are the sound absorbing materials classified? We have various kind of classifications based on how they work, and what is the mechanism involved. Porous fibrous sound absorbers, panel sound absorbers, Helmholtz resonators, and perforated panel absorbers, micro perforated panel absorbers, and hybrid resonators, and each of them they have their own working principle. Okay, so if I have to give up a summary on what is there inside the material which is causing the dissipation of the sound waves. So, this is the typical sound attenuation that is happening. So, here I would like to insist that although there are, when the sound wave is entering, even a hole or an open window can be called as absorbing, but when we talk about passive noise control and sound absorbing materials, we typically talk about the material that are allowing the sound waves to enter in the material, and at the same time the dissipation is happening within the material, so that the reflection and the transmission, both of them are getting reduced. Okay. So, it is not just allowing the material, the sound wave to pass through the material as it is, but it allows the sound waves to enter inside, get dissipated due to some mechanism. And what is dissipation? It is the conversion of sound energy as heat and hence getting lost. Okay. So, when the sound energy gets lost as heat, that becomes dissipation. So, these materials, they allow the sound waves to enter inside, get dissipated and lost within the material. So, both reflection is reduced as well as the transmission. And in these materials, let us see what is that dissipation mechanism that is happening. So, it is for the porous fibrous sound absorbers, we have viscous dissipation that happens. For these other absorbers, panel, Helmholtz, and the perforated panel and the micro perforated panel, the resonance phenomenon leads to the sound attenuation. And for the hybrid absorbers, which is usually a combination of porous materials with a resonance material, you have both the phenomenons operating together to do the sound attenuation. Okay. So, this is a typical sound absorptive treatment that we do, because we want to use these absorbers, we want to stick them to various, because absorbers have to reflect, they can't be standing or suspended in the air in most of the cases. So, usually they are placed with some material backing, so that and because so they have to allow the sound waves to enter inside. So, usually they have some ports. Okay, most of the porous materials, they have ports, etc. So, these ports have to be protected from the dust and other particles, because the performance of the material will depend on that. So, an acoustically transparent membrane such as a mylar sheet can be used. So, it will protect the particulates in the air from entering inside the material, but it will be allowing all the sound waves to enter. So, this kind of treatment can be done on the surface, and then you have the absorber material, and then you have some barrier backing, typically because whatever sound is emitting outside, we want to control that as well. So, we have a barrier installed. So, this gives a better sound absorption treatment. So, with this I would like to close this lecture. Thank you for listening.